Hello, this is section 1.5 for Calc survey, and today we're going to be talking about exponential functions. So a linear function has a constant rate of change. That's what we've been talking about in the previous sections. And an exponential function has a constant percent or relative rate of change. So hopefully a lot of these formulas will look familiar to you. So an exponential function, P equals P initial times A raised to the T, and T representing time. Now A is equal to 1 plus R. So just realize whenever you're given a percent rate, you will make sure that's converted into a decimal. So move your decimal over 2 places to the left and then add it to 1. That's the number that goes here. And then your P initial is what you're initially, so if you were talking about investments, what you initially started with, or your initial population, if that's what you're talking about. Now, if A is greater than 1, so if R is going to be a positive number that you would add to 1, then that's going to become an increasing exponential function. If A is between 0 and 1, so between 0 and 1, that means R must have been a negative number to make this less than 1, making this a decreasing function. So R is the decimal percentage. It can be positive or negative, and that's what we just talked about. So this formula and this formula are exactly the same. Right? But you have to remember that A is equal to 1 plus R. Now another one that you might remember is the compounded interest. So P initial, so in your parentheses here, 1 plus R over N raised to the NT, and that's your compounded. And we'll talk about that here in a minute. So graph the exponential function. This is just a review on how to graph. Basically with exponential functions, we tried to find those 3 points where you get a nice representation of the curve. But you have a graphing calculator, so use it. Okay, and then determine which of the following tables of values could correspond to exponential or to linear functions or neither. So look at your, I like to start with this point and then go back. Work backwards. So it looks like I always look for a common difference first. So did we add or subtract? It looks like we added 1.3, and then, oh, it looks like we did the same thing. And then just make sure you're checking it. Also, don't forget to look at your X values and make sure we're increasing by the same increments, right? Excuse me. So on this middle table, you're increasing by 1 each time. We're good to go. So in this case, to go from 3 to 5, well, we added 2, but we don't add 2 to get 9. All right, so that doesn't work. So looking at it as an exponential, 5 divided by 3, okay, 5/3. If I multiply 5 by 5/3, do I get 9? No. So this is neither. And then this next one, so again, check your X's, we're good to go. Now, what happened to 3 to get 1.5? I cut it in half, and then 1.5, if I cut that in half, I get 0.75. I cut that in half. I think we're good to go. And just make sure you're checking. Also, get out your graphing calculator. There's no shame in checking that what you think's happening. I think it's a really good idea to make sure you utilize your calculator. Okay? But that is an exponential function because you have a common ratio. We're multiplying by 0.5 each time. All right, so here's another example. Find a formula for the number of zebra mussels in a bay as a function of the number of years since 2003. Notice I underlined that. Of years since 2003. That's our year 0. Given that there were 2,700 at the start of 2003 and then 3,186 at the start of 2004. Okay, I see 2 ordered pairs right there, and that's what I wrote. T equals 0. We have 2,700 mussels, and a year later, 3,186. Use that ordered pair. And so then from there I found, and it says, assume that the number of zebra mussels is growing linearly. So I used those 2 ordered pairs to find the slope. Got the slope, and that would mean it's increasing 486 mussels per year. Remember, slope is a rate, and how you solved it will tell you it's the difference in mussels per change in time, mussels per year. Okay, so assume the number of zebra mussels is growing exponentially. What is the percent growth? Okay, so now we got to go back to that section where we talked about percent change or relative change. So you subtract and divide by the initial. So take your two values, and it's growing, so it's going to be positive percentage. Take your two values, subtract them, divide by the initial, and you get 0.18, or increasing 18%. Now that's your R, so you'll do 1 plus R, so 1 plus 0.18. That's your A value. And there's your nice formula. And now you can plug in anytime you want. So remember, if you plug in 2, that would be 2 years after 2003. So be careful. All right, and then example 4, the number of passengers using the subway system fell from this large amount to this large amount during a 5-year period. Find the annual percent decrease over that period. Okay, again, 2 ordered pairs. We have the initial, we have 5 years later, that 392,000. So using this formula, we have the initial, our P initial, that's this 452,000 here. We've got to figure out what that A value is. So we're going to use that other ordered pair to plug it in. So I plugged in T is 5. And I plugged in this 392,685 here, and then was able to solve. So divided, took the 5th root of both sides, and got my 0.972. I'm going to move this up, this little space right there. So the value, and that's what's going to go here, and that gives me my formula. I didn't get the rate though, I just got A. So it's 0.972 equal to 1 plus R, subtract over 1, and now I got my decreasing 2.8% annually. Now, I don't know if you noticed, you might say, Cogswell, in the last problem, we did that whole subtract divide by the original. Why didn't we use that same method? There's a really important reason. In this example, it was over 1 year that we were finding the percent change. That's what allows you to this method, all right? Whereas in this one, it was over a 5-year period. Therefore, you cannot use that percent change little formula. So if it happens to be over 1 year, sure, subtract, divide by the original, you got your rate. But the fact that it was over a 5-year period, you'll have to go the long route, the algebraic route. So amount, plug your other order, and work backwards and solve for A. Okay. Now, I don't know if you can kind of see, but this is leading up. This one was very straightforward. Divide, take the 5th root, good to go. But are you going to be okay if the variable is in the exponent world? And we're going to need to practice that, and that's what's coming in the next section. So while we're doing this video, let me talk you through this real fast. So common logarithmic mistakes. So make sure when you have the log of this binomial x plus 3, you cannot break this up, right? If you were to ignore this part, ignore this side and start with this, if you were to combine these two together, remember it would be log of 3x, and that is not what you started with. Another important mistake students make, you cannot pull this 2 down in front. It can only, if the 2 had been just applied to the x, so x squared, then you would be allowed to pull it down in front. So that's, if we ignored this and started here, you could pull that 2 back up and it would become natural log of x squared. So be careful. Same thing, kind of what we did up here. If you start with natural log of 3x, you can break this up. That is not legal. And then finally, this one I see a lot. You cannot pull 2 down in front. It has to be applied to both. I mean, if I had the parentheses here, if it was 3x all squared, then you would be allowed to pull the 2 down in front. So those are just some very common mistakes that we see a lot, but that's what's coming in the next section. So if you see this and starting to panic a little bit, you'll definitely want to make sure you practice and freshen up on those log problems, okay? Or log problems. All right, please do your homework. Email me if you have any questions.